Okay, so we are going to be looking further into isotopes, and we're going to look at the differences between a stable isotope and something that is considered radioactive. So right now you should have a chart. It's also available to you in the stream if you're at home. But if you're in the class, I have blown up these charts of the naturally occurring isotopes, so it makes it a little easier to see. On there, you will see 3 different colors. You see a gray, a black, and white boxes. If you look at it in the textbook, the actual physical textbook, it would show up as pink, but that just represents those light gray boxes. You can see a snippet here of some things that you'll find on that naturally occurring isotope chart, and we'll talk about those as we get there. Okay, so some learning goals. At the conclusion of this lesson, you will be able to interpret the graph of naturally occurring isotopes. You'll be able to look at the x-axis, y-axis, and figure out pieces and parts of information or characteristics for each of these isotopes, okay? You'll be able to describe the composition of a stable nucleus. You will be able to differentiate between a stable isotope and a radioactive isotope, and a lot of times we can do that by looking at their location on that chart, okay? Picture that you see at the bottom here, these are 3 different isotopes of hydrogen. Okay, only one vocabulary term here, and it is radioactive isotope. So this is any isotope that has an unstable nucleus and decays over time. Well, we know every atom has a nucleus. What does that word unstable mean? We'll learn that. Okay, so let's think about our information that we learned in lesson 13 about isotopes. We know isotopes are atoms of an element that have different numbers of neutrons. So remember, the atomic number is going to stay the same, but our mass number will change, okay? So we're looking at copper. If you look on your periodic table, copper has an atomic number of 29, and copper has a symbol of Cu. Okay, well, let's take a look at what we have here, okay? Let's look first at Cu, okay? Well, B doesn't have the symbol of Cu, so let's automatically cross that out, okay? Again, atomic number of 29. Atomic number of 29. Remember, the bottom number is going to be our atomic number, and the top number is our mass number. So let's go through and cross out anything that doesn't have a 29. Perfect. Okay, what we want to figure out, if we have an isotope of copper, remember the mass number at the top is the protons plus the neutrons, okay? So if we look at the average atomic mass of copper on the periodic table, it's listed at like 63.55, okay? That is going to be our average mass of the protons and neutrons for all of the isotopes, okay? Well, which of these masses that you see here are possible masses of isotopes of copper, okay? Well, it's not going to be 34, okay? And 87 is really far away from the average atomic mass, okay? That's listed on the periodic table. You can choose A and F because their masses are very close to the average atomic mass of copper listed on the periodic table, okay? Just a little review there. Okay, so what you see here, this is the charts. It's a sample. You do have one that shows up as a document in your stream if you need to pick up one and zoom it in, or if you need to print it out, whatever you need to do. Along the x-axis or the bottom, you will see the number of protons. Okay, this is counted off by 5s. So to count, you know, I need to find atomic number 7. You're going to have to zoom in here. Okay. If you have the large paper chart, it's a little easier, okay? Easiest thing to do is use a ruler or a straight sheet of paper to help you mark this off, okay? The y-axis is your number of neutrons, okay? Pay attention. When you get a number from the y-axis, the number of neutrons, that's not giving you the mass number. You have to take your number of protons and your number of neutrons and add them together. Well, what if you are given a mass number of a specific isotope, okay, and you need to figure out the number of neutrons it has first before you can even find it on this chart, okay? So remember, to do that, I take my mass number minus my atomic number, or my mass number minus my number of protons to figure out my number of neutrons, okay? You will notice on this chart, you will see boxes or cubes, whatever you want to call them. They are stacked on top of each other. Those on top of each other from top to bottom, those are all isotopes of the same element, okay? They will have the same number of protons, but different numbers of neutrons, okay? Again, notice this is showing a straight line here, so it's a consistent slope. That line that you'll see here, it's the best fit line. You will see some boxes are falling right on that line, some are not falling on that line. Sorry. If they're falling on that line, we have the same number of protons and the same number of neutrons. Okay. Further away, the larger the difference you have. Okay. The graph of naturally occurring isotopes gives us an idea of how many different isotopes of elements that are found in nature. Some of them only have naturally occurring isotopes. Others have several naturally occurring isotopes, as well as radioactive isotopes that you see here. If you look at the key, the black represents the most abundant isotope of that element. The gray are other isotopes found in nature, so those are naturally occurring. And then the white boxes represent radioactive. Okay. Ones that can only be made in the laboratory are not considered naturally occurring. Okay. Those are the ones that you will see as white. Okay. For the most part, on the right-hand side of your chart, those white ones are made in a laboratory. Okay. The words atom, isotope, and element are interrelated. So all matter is made up of elements. Elements are made up of individual particles that we like to call atoms. All the atoms of an element are identical with this simple exception. Some of those atoms have different numbers of neutrons, okay? An isotope is one type of atom of an element with a very specific number of neutrons, okay? Nearly all atoms have at least one neutron for every proton in the nucleus. So, if you go back and look at that chart, points that lie right on that diagonal line on the graph indicate that isotopes with equal numbers of neutrons and protons fall right on that line. Many of the most abundant isotopes fall where we see 40, the atomic number of 40 and below. They have equal numbers of protons and neutrons. At least one of them does. Okay. Many isotopes have more neutrons than protons. Okay. And this is where we see our nuclei becoming unstable. Okay. The curve that we see on that chart, the curve of our data, the further away we get from the line, you will see a greater number of neutrons than protons. Okay. The more protons an atom has, or the larger it is, the more neutrons it needs in the nucleus for it to be stable. For the largest atoms, this ratio is going to be close to 3 neutrons for every 2 protons, so a 3-to-2 ratio, okay? One way we can think of this is that neutrons are like the glue or the packing material in the nucleus. They help hold those positively charged particles together, okay? A handful of isotopes on the chart are unstable. This means that over time they emit particles from the nucleus, they break down, they decay, okay? The white squares on the graph designate these unstable isotopes. These are also called radioactive isotopes. And this means that some atoms are, and you'll see I have quote unquote lost, okay, over time because they undergo radioactive decay or they spontaneously emit particles from their nuclei, okay? We'll talk more about radioactive decay in the next couple lessons, but when I'm saying they're lost, they don't disappear. Remember, matter can't be created or destroyed. It's essentially, we're using the word lost because it's being changed into a different type of atom, okay? We'll further into that in 15 and 16, okay? Some elements have naturally occurring radioactive isotopes. For example, hydrogen-3, we can call this tritium, is hydrogen's radioactive isotope. Each tritium isotope, which you'll see here on the right-hand side of the screen, it has 1 proton and 2 neutrons in its nucleus. It's very rare. Argon, technetium, cerium, and promethium also have radioactive isotopes. Technetium and promethium are really special. They're not found in nature, but they're all man-made and very unstable. Okay. The isotopes of elements after bismuth. Okay, so bismuth, if you locate it on your periodic table, it's atomic number 83. Its symbol is Bi. Those are all radioactive. Okay. The elements after uranium, okay, 93 and up, were all discovered in a lab and are radioactive. So most of the human-made elements break down really quickly. And some of those have this thing that we call half-life. Again, we'll learn about that further on, but they break down within seconds or fractions of a second. Okay, so let's do this. Let's use the chart to determine how many neutrons you would need to make a stable element with 79 protons. So what you want to do, you want to look on the chart for 79 protons. Okay, so if I have that here, 79 protons is going to be right before 80. Okay, so easiest thing to do is look at this vertical line of 80 and go all the way up until you get to some boxes, and then look one space to the left. Okay, just look one space to the left. Okay, we need to know how we can make a stable element. Okay, since this box is not white, we have to understand that it is stable. Okay, there's only one isotope for atomic number 79, and atomic number 79 is gold. Okay, we need to figure out how many neutrons we need. Okay, so I'm going up and I'm finding my box, and then I want to look all the way over here to the left to figure out my number of neutrons. Again, easiest thing to do is take your piece of paper and slide it up on the screen to help you find this. But if you look at the crosshairs here, that horizontal line, this is at 120, so 119, 118. So we're going to say that we're going to have 118 neutrons, okay? 118 neutrons. So what element is this? Well, we already identified that as gold. So write its isotope symbol. So we're going to write down its name as gold, okay? So I know the symbol is Au, and my atomic number is 79. Well, this top number that goes up here, we have to understand that we have to have 118 plus 79, okay? Well, what is that? 197, okay? So our number at the top is going to be 197. I apologize, it looks terrible. So my symbol is a 197 over 79 Au, and my name would be gold 197. Okay?